Organometallic compounds, these are compounds that contain carbon that is bonded to a metal. The difference in electronegativity between the carbon and the metal is going to determine what type of bond we are working with. Is it a covalent or an ionic bond? If you look at the electronegativity table, I've listed this on eCampus as well. In there, the type of metals that we are going to work with are lithium, copper, and magnesium. Those metals are going to be bonded to a carbon. So when determining the type of bond, you have to look at the electronegativity of the carbon versus the electronegativity of the metal that it is bonded to. Let's consider each one of these cases to determine the type of bond between the carbon and the metal. So carbon lithium, carbon magnesium, and carbon copper in there. Look at the electronegativity of the carbon versus that of the metal. Lithium electronegativity is 1, magnesium is 1.2, and copper is 1.9. The smaller the electronegativity difference, the more covalent the bond is. So here delta En is 0.6 versus here delta En is 1.3. It's always an absolute value. Versus here delta En, it's the difference between both electronegativities. This is 1.5 in there. So you can easily see over here that the bond between the carbon and the copper, this is going to be a more covalent bond. So this one's going to be more covalent. Compared to the carbon magnesium, it's considered to be a covalent bond. Versus the carbon lithium, this has the highest electronegativity difference. So this one over here, since it is 1.5, normally 1.5 or greater, this is considered to be an ionic bond. So the bond between the carbon and the lithium is ionic versus the carbon magnesium and the carbon copper. These two bonds are considered to be covalent. Since carbon is more electronegative than any of the metals, then in this case, if you want to draw the direction of polarization, because once you start the reactions, it's very important to know what is the charge of the carbon. So here I'm just going to call this a metal. And there, all the metals are less electronegative than carbon. This means that the direction of polarization is towards the carbon in there. So this is going to make the carbon a partial negative charge. So now my nucleophile is going to be the carbon. The metal is always going to be a partial positive charge in there because it is less electronegative. Carbon is going to pull its electrons away, leaving it partial positive, and the electronegative cloud is going to be more around the carbon, so carbon is partial negative. So in this chapter, we will be working with carbons that are negatively charged. These carbons that are negatively charged, we call them carb anions. So we said that this bond is an ionic bond and these two bonds are covalent bond. For simplicity, we are going to take out this covalent bond and represent all carbons in a form of a negative charge, not partial negative, negative charge. So whenever you're representing any organometallic compound, take this bond out and represent the carbon in a form of a carb anion. We know that a carbon, to have a negative charge, it needs to have 3 bonds and a lone pair. Okay, the total number of bonds need to be 3. So you can have a triple bond in there, or you can have a double bond and a single bond, but the total number of bonds need to be 3 in there. That is going to be balanced with the charge of the metal, and the metal normally should balance the charge of the carb anion in there, or whatever is coupled to the metal needs to balance the charge of the carbon ion. So this is how we are going to represent organometallic compounds. So when the metal So when the metal is lithium, we are going to call it organolithium reagents. When it is magnesium, these are Grignard reagents. And when it is copper, this is Gilman reagent. In all of these organometallic compounds, the carbon is always a negative charge. And the carbon can either be sp3 or sp2 or sp. This makes these reactions very important reactions in there because I can vary the hybridization of the carbon. So I can have an sp3 versus an sp2 versus an sp hybridization that is connected to the lithium. So as we said, the bond over here is ionic, so we normally represent it. We take the bond out and we represent it. So this is similar to that. We represent now the carbon being negative, and I prefer this representation in there. The reason why I want you to represent it like this, because once we start reactions, you want to know where is your nucleophile. And in this case, the carbon over here is going to be our source of electrons. So the arrow is always going to start from the carbon. The carbon that is directly connected to the metal is the one that has the lone pairs and the negative charge. Always the metal balances the carb and ion. So because this one here is a negative, then the lithium is going to be positive. Anyways, lithium is in a group number 1, so it is a +1 charge in there. Whether you're working with an sp, sp2, or an sp3 hybridization in there. Coming to the Grignard, the bond between the carbon and the magnesium, we said that this is a covalent bond, but the bond between the magnesium and the bromine, this is an ionic bond, okay? So this bond over here, again, look at the electronegativity difference. This is going to be an ionic bond in there, but this bond over here is a covalent bond. Covalent bond. For simplicity, we are going to represent it in a form of its charges in there. All charges need to balance out to be 0 in the Grignard. This is going to make the carbon negative. Magnesium is a +2. It's in group number 2 in there. And the bromine is a -1 charge. All of the charges balance up to a 0 charge. So now if I look at it like this, I know that the source of my electrons is going to be the carbon with the negative charge. Whether the carbon is an sp3 hybridization or an sp2 hybridization in there, or even an sp hybridization. Gilman is the most covalent bond between the copper and the carbon in there. For Gilman, you have two R's that are connected to a copper. And then the bond between the copper and the lithium, this is considered to be an ionic bond in there. The bond between the copper and the carbon, this is a covalent bond. So you have here two covalent bonds and you have an ionic bond in there. But again, for simplicity, we said go ahead and take out the covalent bond represented in a form of a charge. Charges need to balance out to 0, so carbons need to be negative charges each. Copper is positive and lithium is going to be +1. This is called a Gilman reagent. Another name for it is an organocuprate reagent. We're going to go with both names. All of these organometallic reagents, they react with water because the metal that they are made of, the metal over here is in a form of an ion, and that metal reacts violently with water. So this is why whenever these reagents are used, we prefer to use a water-free solvent. The most common solvent that we use is ether solvent, or it's a diethyl ether. These two are the same, and it's actually two ethyl molecules that are connected by an oxygen. There are other solvents that we use are water-free, like THF, but this one is a better solvent because it can evaporate at a very low temperature and we can get rid of it. When you want to name these organometallic reagents, all what you need to do is name the carbonate chain first, and then the metal comes at the end. So here I do have 4 carbonate chains, so it's going to be a butyl, and then you put a lithium. There is no space between the carbon ion and the metal name. Over here I do have a vinyl group. So this is going to be a phenyl. You do have your magnesium, and then it's going to be a bromide in there. Here I do have magnesium and two R's next to it, but this is going to be my Grignard reagent over here. This is not a Grignard reagent. This is a Grignard reagent there. Here I can easily see that the magnesium is coupled with two carbons in there. So I have two types of carbon ions. I have this carbon over here and this carbon over here that are negatively charged. And then the magnesium is two positive. Here's an example of how to name Gilman reagent. Gilmans are always going to have R's that are the same, two of them. So please couple them with a prefix di. So there's going to be a dipropyl, and then you name the metal that is higher in electronegativity than the lithium at the end. This one is lower in electronegativity.